Graphs. No, those things you're thinking about are actually plots and charts. Okay, in this introduction, we're going to go through quite a few terms. Graph or graph. Vertex, vertices, same as matrix, matrices. Edge, face, cycle, loop, multiple edges, simple graph, connected graph, isolated graph, degenerate graph, complete graph, subgraph, bridges, isomorphic graphs, planar graphs, and adjacency matrix. Yes, matrices, they're back. Okay, let's get through some of this terminology. So if we have a graph, you're going to have lots of little dotty things like this. And they are called, that's one of them is a vertex. And if you have more than one, you have vertices. All right, and they are connected by, let's change colors a lot today. That's an edge. And then this is a face. Okay, because you can see you got things there. But also, this is a face. So, important trick. The outside is a face. I've done another video, which will come out soon, which explains why the outside is a face. So this graph has two faces, one on that inside here, and then one all the way around on the outside. So two faces there. Don't forget the outside one as a face. All right, so if we've got some vertices connected like this, we've created a cycle. And we have a face in there. All right, so we've created a face, but we've got three vertices here. Now, if we look at a similar situation, and they're easy to confuse, and sometimes the terminology has changed over the years, this, there's a face in there, but this is a loop. All right, so you can see we've only got the one vertex for the loop, but we've got more than one vertex for a face. All right, for a cycle. Now, the other thing to note is this thing, you got two vertices. Normally, you only connect them with one thing in certain situations, but that's what we call a multiple edge. Edges. So if we're talking about multiple edges, there's certain situations where you don't want to do that. So again, you also don't want to have loops or cycles sometimes. All right, let's look at a simple graph. And there's basically two rules here. No loops, no multiple edges. You can have cycles. All right, so let's imagine we've got some vertices here connected up like so. We've got a cycle and we've got a face. So here we've got a face here. That's okay because we've got that cycle around the outside of it. But this, not allowed, that would be a multiple edge. And this, not allowed, no, because that's a loop. Okay, so a simple graph does not have those things. All right, and then we have the idea of a subgraph. So imagine you've got a graph like so. Let's just do something like that. Now, we could say, look, I'm just going to take a part of that graph. I'm going to take these three vertices, and we can see that that's exactly the same as this part. So what we have here is a subgraph. So this is a subgraph over here. You can see that we've just taken part of the graph and used it over here. And you could do other subgraphs. You could do, let's take just the whole squarey bit over here. Look, there's a subgraph like that. It's got to include the same sort of bits of it. I mean, if you've got the four vertices, then they've got to have the same connections. Otherwise, it's not really the same thing. But there you go, subgraph. It doesn't really come up in questions. Okay, so now we need to look at connected graphs. And funnily enough, a connected graph is just one where everything is connected. So you might have to do a thing called a bridge. So like this, you've got something like this, and they're all beautiful in a nice graph over here, and then you have something like this. All right, so obviously these two graphs are not connected, so you do that. Okay, so every vertex is included. All right. All right, so this thing is called a bridge, but I don't know why they mentioned that. It's just not really that useful, but it's connecting those two graphs together. So everything, every vertex is included. So you can go, if I was here, I could, travel across to here. That's what a connected graph is. All right, let's talk about isolated vertex. And so imagine you've got all your friends over here, they're having a good time, they're all connected together in a nice friendly network. And then there's one over here. This dude is an isolated vertex. Got no friends. And that leads us to another situation. So if we have a degenerate graph, that's just like that. So no edges at all. All right, and that's what a degenerate graph looks like. All isolated vertices, no edges. All right, let's have a look at the idea of a complete graph. So this means every vertex connected to every other vertex. Now the simplest case of this is actually you've got two vertices like this, connected with one edge. Then if you went to the situation of three vertices, you'd have three edges like this. If we had four, you need to have this one and this one as well. And then five is my favorite one because it's the pentagram. Like that. Now, interestingly enough, this forms a series of numbers. This is one edge. This one is three edges. This one is 6 edges. And this one, 10. And if you kept going, you would be able to see that this is actually a series of numbers called the triangular numbers. Triangular numbers. Maybe I'll do a separate video about that one day, but you can see here we're +2, +3, +4, so you can imagine that the next one is going to be +5, and that is true if you have a hexagon. Interesting thing to note, all these guys on the left are planar and non-planar. So that probably brings us to our next slide. What does planar mean? All right, now let's have a look at planar graphs. So here we have no crossovers, or you might want to call them intersections. Okay, so if you have 4 vertices like this, you can connect them with 1, 2, 3, 4, 5. But if you do the 6th line, you're crossing over this point here, and we don't want that. So we can redraw that graph. I'll just show you on a graph below. If I go 1, 2, 3, 4, and then I connect them up like so, I can take this last line instead around the outside, and it's still the same graph. And we can do that, prove that by, look, this one's got 3, degree of 3, degree of 3, degree of 3, degree of 3, and that's the same here. Look, there's still 3, 3, 3, and 3. So they are all exactly the same graph, exactly the same connections. So these two graphs are actually, these are isomorphic, which means they're the same shape. Basically, morph means shape. All right. Now, if you start with the next one on our graphs, which is our friend the pentagram, like so, messy as it is, there's no way to do that. You can try as much as you like. It is a very common exam question to give you something like this, and I'll show you in the exam questions later. They've given you everything except one, so the cannot be planar here. But this is planar. And I'll let you play around with that and see if you can work out exactly how you do it. There's two sort of tricks to these things. Often, like as you saw on the left over here, a neat trick is just to take a line on the outside, but sometimes it's quite useful to grab a vertex and sort of move it into the middle as well. That's my only hint I'm going to give you, but that's how you can make that graph a complete graph. -1 will be planar for the pentagram only. Okay, we're going to look at an adjacency matrix for this network we've got on the left. As you can see, we've got a matrix set up. This is pretty much a communication matrix, which you may have done before when you watch my other videos. I'm sure you're all doing. Viewer count certainly agrees with that. Now, A to A, we can put a 1. Let's look at A to B. We can put a 1. Then we can look at A to C. We can't do that, so we put a 0. Can we go A to D? Yes, we can, so we can put a 1. And then we look at A to E. We can't do, so we put a 0. Now, just like with the communication matrix, since there's no arrows, the thing is symmetrical, so the first row is the same as the first column, but we're going to do this anyway, the slow way. So let's do this slowly. Let's do B to A, 1. Then we can do B to B. There's no loop, so that's a 0. If my pen's working. Then we can go B to C. We can do that. That's a 1. Then we can go B to D. We can do that. That's a 1. B to E, we can do that. That's a 1. Again, second row is the second column. That's the way these things work. C, well, look, let's not go too slowly here. C only connects to B. 0, 1, 0, 0, 0. Then D. Now D connects to A, B, not to C, and twice to E. All right, so it doesn't have any loops as well. So D to A, 1, D to B, 1, D to C, no, D to D, no loop, and D to E, 2. You can have a 2, it's okay. And then E, you can see obviously can go to B and then just to D twice. So E does not go to A, E does not go to E does go to B, E does not go to C, E goes to D twice, and there's no loop. All right, so if we just grab our highlighter here on our classic leading diagonal, you can see there's one loop, and that's shown by that value there. Everything else, the zeros mean no loops. All right, so non-zero leading diagonal equals loop. All right, that's just a translation of what I just said there. So there's a 1 there, no loop, no loop, no loop. That's all we're saying for that. And again, if you look at the first row, 1, 1, 0, 1, 0 is 1, 1, 0, 1, 0. It's the rows are the same as columns because of symmetry. We can see the same thing here. Row and column are the same. And you know, third row, third column are the same. Check it out. Same values if you read them. And same, if we just grab the last one. So look, fifth row goes 0, 1, 0, 2, 0, 0, 1, 0, 2, 0. Okay, that's what the symmetry means because there's no arrows. And that's an adjacency matrix. Which one of the following graphs is not a planar graph? Quite obviously this one. That's the pentagram. It is evil. But in all seriousness, it is that one because the pentagram is the first complete graph that cannot be made planar. If you look at A, you can get rid of that line there and just put it around the outside. If you look at E, there's no crossovers, so that is definitely planar. These B and C are incomplete pentagrams, so they've had 2 lines removed. It makes it quite easy. I'll leave it as a bit of a puzzle for you guys to work that one out, why they can actually be made planar. Though it says planar graph here, it's talking about faces, vertices, edges around the place, so it looks like it's a hidden way of saying use Euler's formula. So V minus E plus F equals 2. They've given us that F equals 5, so we know V minus E plus 5 equals 2, so we've just got to worry about this. Now, for this whole statement to be true, we want this whole thing, V minus E, to be minus 3. So we want 3 more edges than vertices. And if you do all your calculations, it's E. Which one of the following graphs contains a loop? This one, because you can go from here and you go around like that. That's the loop. Okay. This case is multiple edges. This is 2 lots of multiple edges. That's 3 lots of multiple edges in D. And this is a cycle, not a loop. So the answer is B. All right. It says 2 graphs labeled graph 1 and graph 2 are shown below. The sum of the degrees of the vertices of graph 1 is, all right, let's do the sum of the vertices. That's 3. Obviously, they're all the same corner, so that is 12 in total. 3 times 4. Obviously, each one of these has a degree of 2, so that's 2 times 6. This is also going to be 12, so it is equal to the sum of the degrees of the vertices of graph 2. Done. All right, adjacency matrix. So they've already given us the leading diagonal, and you can see when we got a 1 here, that means you got the loops. So that's WW, that's Z to Z. So loops are 1 on the leading diagonal. Now, if we let's just fill in the rest of the adjacency matrix while we're here. So now, remember, no arrows, so this is going to be symmetrical. So if we start at W, we can go to X in 2 ways. If we start at W, we can go to Y in 2 ways. And again, we're going to start at W and go to Z. We can do that in 1 way. Now, if it's symmetrical, row equals columns, so 1, 2, 2, 1 becomes 1, 2, 2, 1. It's just a thing. First row is same as the first column. Now, we just need to look at X to Y. When my razor is working. So X to Y, there's just 1. And X to Z, there's just 1. So 2, 0, 1, 1, 2, 0, 1, 1. Second row, second column, same thing. That's symmetry. So we're going to have to work out, the next one is just Y to Z. So if you go Y to Z, there's just 1, which means there's just 1 there, and we completed our graph. All right. There are 16 elements when complete. Of the 12 missing elements, that's the red ones, a little bit of a trick there, of the 12 missing elements, that's the ones I've done in red, 8 are 1 and 4 are 2. Actually, that's correct. A. If you check the rest, the main thing to note was that it does not include the leading diagonal. All right. Our old friend, the pentagram. Believe it or not, it's nothing to do with Satan, it's everything to do with Pythagoras. Now, the edges are removed so that the graph will have the minimum number of edges to remain connected. The number of edges that are removed is, all right, because it's a complete graph, you know it's actually a triangular number. So if you remind yourself, the triangular numbers are 1, 3, 6, 10, 15, 21, etc., etc. So when you've got 5 vertices, 2, 3, 4, 5, you've got 10 lines. And everything needs to be connected, so you can actually keep getting rid of lines until the whole thing's connected. And basically, you can get rid of everything in the middle like that, and then one of these outside ones as well. Get rid of all that, and you've got 1, 2, 3, 4. it'll still be all connected, so you're actually getting rid of 6. Bit of a trick there that you might have forgotten to eliminate one of the outside ones as well. All right. So basically, you're taking a complete graph into a tree. So it's a complete graph into a tree, a spanning tree.